Okay, let's dive right into this explainer. We're uncovering an invisible, dynamic web of light currently orbiting Earth that is fundamentally changing how the internet works. When you think of Starlink, you probably just picture that little dish on your roof, right? Maybe a satellite zooming across the night sky. But there's an entirely hidden petabit-class network operating right above our heads, and it's powered entirely by lasers. Today, we're breaking down how SpaceX built a literal optical mesh in the vacuum of space and why it's about to become the infrastructure for a whole lot more than just your home Wi-Fi.
To start, let's clear up a massive misconception about how you actually connect to this network from your backyard. Because, we hear the phrase space lasers, and it's incredibly easy to imagine your home dish firing a concentrated beam of light directly up into the sky. But that's absolutely not what's happening. You aren't pointing lasers at satellites.
You actually connect via standard radio waves. It's the satellites themselves that use these true space lasers to talk to each other up in orbit. The key concept here is the Optical Inter-Satellite Link, or OISL. Essentially, it's a laser communications path that moves high-capacity data directly between moving spacecraft. It's a space-to-space conversation. Your dish talks to the satellite using radio frequencies, and then that satellite turns around and shoots your data across the entire constellation using an incredibly narrow beam of light.
This is a brilliantly designed two-layer architecture. You have a massive radio network facing us down here on the ground, backed by a hidden, insanely high-speed optical network flying above it. Think of the radio links as the local roads connecting your house to the highway, and those optical inter-satellite links, those are the superhighways in space, routing traffic all across the globe before it ever needs to drop back down to a ground gateway on Earth.
Section 1. Tracking the laser mesh. Let's pull back the curtain on the sheer scale and extreme engineering required to make this optical layer function. According to Starlink's 2025 progress report, there are over 13,000 bidirectional laser links currently forming a global petabit-class mesh in low Earth orbit. 13,000! This isn't just some science experiment or a small-scale demo anymore. This is fully operational, commercial infrastructure serving residential, maritime, aviation, and government customers all over the world every single second of the day.
And they are incredibly fast. Each V2 mini satellite carries 3 of these optical terminals, blasting data at up to 200 gigabits per second without dropping the connection. Having 3 of these links means a single satellite can simultaneously connect to multiple neighbors in orbit, constantly sending and receiving massive amounts of data in a continuous, unbroken chain.
But here's where it gets mind-boggling. The sheer difficulty of keeping a narrow beam of light perfectly locked onto another satellite zooming through space is insane. Honestly, it's like trying to hit a moving target with a laser pointer while you're riding a roller coaster. The extreme tracking engineering here is off the charts. These optical terminals act like micro-telescopes. They have to find, acquire, and lock onto each other while flying at a blistering 27,000 kilometers per hour, across distances of up to 1,000 kilometers. They're managing vibration, thermal shifts, and perfectly stabilizing the beam, all while both spacecraft are just tearing through orbit.
Section 2. Escaping ground station limits. So why go through all this engineering trouble instead of just bouncing signals directly back to ground stations on Earth? Well, by operating as a moving packet network, the system can dynamically route a multi-hop path right across the constellation. This lets it completely bypass local ground station limitations or overloaded gateways. Imagine you're on a plane flying over the remote Pacific Ocean. Obviously, there are no ground stations out there, so the plane sends its data up to the nearest satellite via radio. Then, that satellite uses the laser mesh to instantly hand that data off to another satellite and another, bouncing sideways across different orbital planes through a dynamic spatiotemporal mesh. Using microsecond handovers, the network calculates the absolute optimal path and shoots the data hundreds of miles until it binds a satellite with a clear line of sight to a ground station back on land.
And this brings us to a massive latency advantage. Instead of light winding its way through bent glass cables here on Earth, it can shoot in a perfect straight line through the vacuum of space. Here is an amazing physics fact for you. The speed of light in a vacuum is actually about 30% faster than it is when traveling through physical glass fiber cables on Earth. Add in the fact that terrestrial fiber often zigzags through landing stations and messy metro networks, and you start to see why a direct laser beam cutting through the vacuum of space can actually deliver data faster than underground cables in so many long-distance scenarios.
Ultimately, this hidden mesh is the secret sauce. It allows Starlink to serve maritime vessels out in the deep ocean, reroute around disaster zones, and drastically increase overall network capacity. If a hurricane knocks out a local gateway on Earth, the network simply uses the lasers to reroute the traffic to a gateway hundreds of miles away in just a matter of milliseconds.
What you should really take away from this is that these space lasers totally decouple our internet access from local ground infrastructure.
Section 3. Commercializing space lasers. The really crucial point here is that SpaceX is no longer keeping this revolutionary technology just for themselves. They are now offering compact mini laser terminals for third-party spacecraft. These little guys are capable of holding 25 gigabit per second optical links across vast distances up to 4,000 kilometers. This essentially allows other satellite operators to just plug directly into the Starlink network in orbit. They've taken a technology they mastered through mass production and turned it into an off-the-shelf commercial product for the rest of the space industry.
Think about what this means for things like Earth observation. Satellites can instantly beam critical wildfire or disaster data directly into Starlink's mesh instead of waiting to fly over a traditional ground station. Right now, a weather satellite might spot a wildfire, but it literally has to hold on to that data until it physically flies over an authorized antenna on Earth to download it. By integrating a Starlink mini laser, like the company Muon Space is doing for the Firesat constellation, that imaging satellite can instantly shoot the image sideways into the Starlink mesh, delivering that alert to first responders on the ground in real time. It completely removes the delay between space sensing and software delivery, a real game changer.
Section 4. The Orbital Data Center. Because, as it turns out, just transporting data is only the beginning of this story. Check this out. A staggering February 2026 FCC filing outlines a proposed system of up to 1 million satellites. 1 million! This would turn the laser network from a simple transport layer into actual orbital computing infrastructure. This application, which was accepted for filing by the FCC Space Bureau, strongly hints at a future where satellites don't just route your internet traffic, they actually process and store data right there in space.
It's amazing to map out this journey from today's operational broadband backhaul to a future where SpaceX functions as a shared space-based data utility. We start with what we have today, right? The broadband backhaul routing internet traffic. Then we move to the commercial integration of mini lasers for third-party operators. And finally, the boldest step of all, an orbital data center for cloud compute customers. Imagine processing massive amounts of data in orbit, connected by incredibly fast lasers, before sending only the vital, finished results back down to Earth.
Parallel to this commercial expansion, we have the Starshield program. This uses the exact same laser heritage to build highly secure, hard-to-intercept network layers for national defense. Because these laser beams are incredibly narrow and pointed directly at another spacecraft, they are vastly harder to intercept or spoof from the ground compared to broad radio broadcasts. This provides a level of resilient, sovereign routing that government and defense clients absolutely require, drastically reducing their reliance on vulnerable ground stations.
So, as they transform these lasers from an internal, proprietary feature into a platform for all of low Earth orbit, it leaves us wondering just how far this optical web is going to stretch. What started as a clever engineering workaround to avoid dead zones in the ocean has evolved into a petabit-speed, microsecond routing backbone in the vacuum of space. If other spacecraft, cloud providers, and global sensors all tie into this single mesh, it fundamentally redefines how Earth communicates. Will we look back at this decade as the moment humanity officially laid the physical, optical foundation for a true interplanetary internet? Well, it's a fascinating thought to leave you with. Thanks for joining me on this explainer, and I'll catch you on the next one.